Hi friends, this is Chef Jin Academy. So welcome to another amazing tutorial. In this video we are going to be looking at the design of rectangular beam, and we are going to be using the Eurocode approach. Before we go into the design, you might ask me, what do we call a beam? So in structural engineering, a beam is a linear structural element that is used to resist bending and shear force imposed majorly from the slab. So practically, a beam can actually be in two forms. You can have a flanged beam and you can also have a rectangular beam. Flanged beam can either be a T-beam or an L-beam, depending on the way the slab is being connected to it. So where can we now find a rectangular beam in practice? A rectangular beam can actually be found in practice, especially in the roof part of the structure. So you can say a roof beam can be considered to be a rectangular beam if it is not being attached to any slab. Let me show you a typical roof layout that shows roof beams that can be considered as rectangular. Then I will also show you another layout where you can consider part of the layout to be a flange beam. Plan here is showing a typical roof layout. You can see that in most part of the roof there is no connected slab, because you can see this cross line. This cross line is trying to show a void area, so that means there is no suspended slab. So in that case, that means all the beams that have been attached to all these columns are said to be a rectangular beam because there is no slab attached to them, so it's going to form a rectangular cross section. But if you look at this part of the slab, you can see that this beam in the front part of the slab of the layout is being connected to a slab. The slab is actually a cantilever slab, so this kind of beam is not going to be the beam you are going to design here is not going to be a rectangular beam because it is now connected to a slab. So this kind of beam is going to be a flanged beam. Then another drawing here is showing the floor layout. You can see that this beam being attached here are connected to slab that are divided into panels ranging from panel 1 to panel 12. So all these kind of beam are designed as flange beam because they are connected to slab. So this beam that I highlighted here will be designed as a T-beam because it has a slab at the left hand side as well as the right hand side part of the beam. But when the beam has a slab in only one part of the beam, then you can consider that kind of beam to be an L beam, even though it's flange beam, but you can still have T beam or L beam. Let us now discuss the procedure of design of a rectangular beam based on the Eurocode. So the procedure of design can actually be summarized using the table that I gave here. So you are going to start by trying to carry out the analysis of the beam, majorly to determine the bending moment as well as the shear force. So in beam, you are designing against bending and shear. So but according to the Eurocode 2, you need to determine the concrete class for the beam. So the concrete class must actually be less than class 50/60. The reason for this is if it is higher than that, Eurocode recommends some change in formulas that are considered to be special case consideration design. If your class of concrete falls between the 50/60, which is what we used to have mostly in practice, then the next thing you have to do is to determine the value of K. This K is actually dependent on the moment, which is given by moment over BD square FCK. FCK in this case is the characteristic compressive strength of concrete, because I've already explained that the Eurocode is actually based on the cylindrical strength of concrete. So FCK must be based on the compressive cylindrical test of concrete. Then after that, you have to determine the K prime. The K prime depends on the amount of redistribution allowed. So most of the time we allow for 15% redistribution, Once you determine K prime, you now need to determine if your K you calculated in the step above is less than or equals to K prime. If your K is less than or equals to K prime, that means you go ahead with the design without providing compression reinforcement. So the introduction of compression reinforcement now brings us to the types of beam that we have based on reinforcement. We can have a singly reinforced beam. We can also have a doubly reinforced beam. I'm going to explain that in the next slide. So, but when your K prime is greater than your K, then in that kind of situation, you have to provide compression reinforcement. But in situation when there is no need for you to provide compression reinforcement, the next thing for you to do is to determine the lever arm Z using this formula, and the value of this lever arm must always be less than or equal to 0.5 multiplied by the effective depth of the beam. Then you calculate the tension reinforcement required. You now check if this reinforcement is greater than or equals to the minimum reinforcement. Then you also check if the reinforcement is greater than or equals to the maximum reinforcement in which the concrete section can take. I've already made a video on minimum and maximum reinforcement in column, beam and slab. You can check out the link in the top right corner of this video. If your beam requires a compression reinforcement, what you have to do is also you go ahead and determine Z, but in this case, in the formula for the lever arm, you are going to use the K prime instead of using K. Once you determine the Z, you go ahead and determine the number of required compression reinforcement. Then you calculate the required tension reinforcement. You follow the same process by checking and ensure that your reinforcement is greater than the minimum required reinforcement for that section, and also less than the maximum required area of reinforcement for the section. Before we take a couple of examples, let me discuss a little about singly reinforced and doubly reinforced beam. This diagram represents a singly reinforced section and a doubly reinforced section. In a singly reinforced section, the beam is being subjected to tension only. So in that case, you need to provide your main reinforcement only at the region where you have the tension. In this case, the tension region is the bottom part of the beam. So that is why you see that we have about 4 number of reinforcement at the bottom. But at the top, there is no need for us to provide a compression reinforcement. But due to detailing, we have to allow for nominal reinforcement at the top. Also, we need reinforcement to hold the shear links that we are going to provide. So that is why we provide the angle bars, and this angle bar is actually equals to the area of the minimum required reinforcement. But in case of a doubly reinforced section, this is when the beam is subjected to both tension and compression. So in that case, you need to provide reinforcement for the tension part, which is what we have in the bottom part here. You can see we have a couple of reinforcement, about 8 numbers of them, 4 in each layers. Then if you look at the top part of the beam, we have what we call the compression reinforcement. So this compression reinforcement is, you can see that it's much more higher compared to the minimum. It's just because compression reinforcement is required in the design of a doubly reinforced beam. In a singly reinforced beam, you only have one effective depth. The effective depth is the distance between the compression part of the beam to the middle of the tension reinforcement. So you can see that the middle of the tension reinforcement here to the compression part of the beam. Then the effective depth of the compression reinforcement is the distance from the middle of the compression reinforcement to the top part of the beam. So let's now move to the step. Let us show ourselves how you can practically design a rectangular beam. Steps in beam design. The first step is to determine your design parameters. These design parameters are what you need in order to carry out the design, and they are subject of the concrete. We are designing a reinforced concrete, so you need to know the property of the concrete as well as the reinforcing steel bar. So this design parameter started from the FCK. FCK is actually the characteristic cylindrical strength of concrete. In this tutorial, we are going to be making use of 20 megapascal, which is the same thing as 20 Newton per millimeter square. If you note, you can see that the class of concrete we want to use is C50/25, which is actually less than 50/60, as I've explained in the previous slide. So in that case, that means we can use the normal design formula to calculate our required reinforcement. The next parameter here is the characteristic strength of steel, the FYK. It ranges between 400 to 600 megapascal. So we are going to be using 410 Newton per meter square. The next thing is the size of the beam. The size of the beam in this case, assuming our beam is having this shape, this is the B part of the beam, this is the H part of the beam. So the B part of the beam is the width of the beam. We are assuming our beam to be 230 beam. Then the height of the beam, assuming 450. Then from the height, we can determine the effective depth. The effective depth is equals to the cover to the reinforcement minus half diameter of bar minus links. In this case, we are assuming a cover of 25, then a bar diameter of 16 mm, links of 10 mm. If you do the mathematics, you are going to end up with 407 millimeters as the effective depth of the beam. Then we are using 15% redistribution. That means our del is going to be 0.85. So before we move to the second step, if this is your first time on this channel, kindly hit the subscribe button, turn on the notification. If you have been watching my video but you've not been subscribing, kindly do so, as this will help other people to find this video and they are also going to learn from it. The next step is to establish the required shear force and bending moments in which the beam is resisting. This can actually be determined from the beam analysis. I have a video on how to analyze beam using Beamax. You can check out that video on the top right corner. I leave a link in the description of this video. This is a typical section of the beam. B is the width of the beam, H is the height of the beam, L is the length of the beam. I've already determined B to be 230, H to be 450. Then we've determined our effective depth to be 407 millimeters. So let's assume that this is our beam and this beam is loaded as is being showed in the diagram. The analysis of this is one of a beam that I've analyzed using Beamax. So we can say that the summary of the beam is giving us the maximum span moment on the beam is 96 kilonewton meters. The maximum support moment for the beam is 153 kilonewton meters. The maximum shear force is 298 kilonewton. The reason why you are having a span and support moment is because the beam that I analyzed is a continuous beam. So in that case, you have span, you have support moment. So let's say we want to design for the span moment. So now that we have the bending moment and the shear force diagram, we are going to be discussing about the design against the bending part of the loading effect, which is the bending moment. So the next thing you have to do is to determine the K and compare this K to K prime. So the formula for K is giving us moment over BD square FCK. You already know the meaning of BD and FCK as well as the moment. If we are designing for the support moment of 96.58 kilonewton meters, you are going to end up with a K value of 0.127 if you substitute B to be 230 and D to be 407 respectively. Then the next thing is your K prime is actually equals to 0.167. This is from the moment distribution ratio formula that we have in the previous slide. You can now see that the value of K in this case is less than K prime. The meaning of this is when K is less than K prime, then there is no need for us to provide any compression reinforcement. So that means our beam is simply singly reinforced. But in case when K prime is greater than or is less than K, then you have to provide compression reinforcement. So since the first condition is satisfied, we don't have to bother ourselves with compression reinforcement. We move forward and try to determine the tension reinforcement. So the next step we have to follow is now to determine the lever arm Z. So the lever arm Z depends on if there is compression reinforcement. Then in that case, your Z is equals to D over 2 into 1 plus square root of 1 minus 3.567 K. This value must always be less than 0.95 D. But if you have compression reinforcement, that means instead of using K in the Z value, you are going to be using K prime. So substituting the value of K from what we obtained in the previous slide, then K is going to be equals, Z is going to be 0.87 D. If you substitute 407 millimeters for D, then you are going to end up with Z equals 354.1 millimeters. So then, since Z is less than 0.87 is less than 0.95 D, then in that case you don't have to bother with the next step. So that means our Z is 0.354.1 millimeters. So the next thing you have to do is to now determine the area of tension reinforcement. This area of tension reinforcement, you have to compare it with the minimum required reinforcement and the maximum required reinforcement. So doing that, the area of reinforcement is given by this formula based on the Eurocode using their partial factor of safety for concrete and steel. So substituting for M, substituting for Z, substituting for FYK. FYK is 410, which is the characteristic strength of steel. Then you are going to end up with an area of 764.64 millimeters square. So this is the required area of reinforcement based on the moment we are designing against. We now have to provide a reinforcement that is slightly higher than this required area of reinforcement. Then the formula for providing reinforcement for beam is equal to the cross-sectional area of reinforcement, which is the same thing as pi times diameter of bar square over 4 multiplied by the number of reinforcement you want to have. In this case, we are assuming a bar size of 16 mm. Then in that case, you are going to end up with an area of 201 as the cross-sectional area for 1 bar. Then if we want to use 4, because we have to provide something slightly higher than the required, so we are assuming 4 number. Therefore, the area we are going to obtain now is going to be 804 millimeters square. This area we got here is slightly higher than what we have in the required. So you compare the required with the provided, it must be slightly higher. Then we move forward from here. We now have to compare this required reinforcement with the AS minimum as well as the AX maximum. If you compute this formula based on the Eurocode, the AX minimum should be equal to 125 millimeters square. Our provided reinforcement is greater than the AS minimum. That means it satisfies the condition. Then the next thing is to compare it with the AX maximum. Substituting B and H of the beam for AX maximum formula, you are going to end up with the maximum reinforcement in which the section can take is 4140 millimeters square. So that means based on the moment that we obtain, providing a reinforcement of 4 number of 16 mm bar is going to be sufficient for the beam. Though this is the step-by-step process in which you are going to follow in order for you to be able to design a rectangular beam based on the bending moment. So because our beam does not require any compression reinforcement, then we don't have to go to that part of the compression reinforcement part. Let us now move to the detailing part. The detailing of the beam is going to go like this. You have the bottom reinforcement, then you see the number is 4y20 because from the area of reinforcement calculated we have 4 number. But we don't need to provide any compression reinforcement, but due to the nominal reinforcement that we have to provide at the top, so that's why we provided 2y16 at the top. So the cross-sectional area of the beam is going to be like this. So we have 4 number of 16 mm at the bottom and 2 number of 16 mm at the top. Let's assume that your reinforcement required compression reinforcement. What you have to do, you have to determine the area of tension reinforcement as well as the area of compression reinforcement, and you compare it with the AS minimum and AX maximum. It's just following the same approach. The compression reinforcement is given by this formula. We already know K, we know K prime, you know D and D prime. Substitute your values, you get the area of compression reinforcement. The area of tension reinforcement is also given by this formula. Substitute your parameters and then you get the area required. Then you have to compare this, you have to provide an area just like we did in the previous slide. Then you compare the area with the AS minimum, you compare the area with the maximum amount of reinforcement. So these are the ways in which you can provide the reinforcement. You can design a beam, a rectangular beam, against bending effect. I hope you learned 1 or 2 things in this video. If you love what I've explained to you, kindly hit the subscribe button, turn on the notification for this video. You can comment and give me example on the course, on the kind of video you want me to make in the future. Thank you. See you in the next one.